Hey all, it's me again. Again, sorry to do this. I will try to be quick, cut to the point here. This is typically a set of notes like yesterday, hopefully, that people find pretty easy. It's not the worst day for me to not be there um, to ask questions and things, but obviously, hopefully, I'll be there tomorrow. Um, but you can see at the top here, it's called vector valued functions. We introduced vectors a little bit yesterday, talked about what they were, worked with them briefly. This now kind of gets at the calculus involved with vectors. So you'll see at the top here where it says the limit of vectors. R of t a lot of times is defined as your vector. So when I tell you that R of t is equal to, and then you're going to see this vector notation, that component form of vector notation we talked about yesterday. It's also parametric in many ways, where this is my x position in terms of time, this is my y position in terms of time. Um, but that's our vector. You can think of it as multiple ways, parametric or vectors. If I want to find a limit, what this is simply just saying is if I have my time approaching some constant, then f of t, I'm going to just figure out what that limit is. That would give me what my x position is approaching at that particular time. If we went ahead and then found out what my g is approaching at that particular time, that would just tell me what my y position is approaching at a particular time. Okay. It really is pretty straightforward. It's really pretty easy to where if I gave you this vector or this parametric equation, again, we can think of them as one and the same, that my position at any particular time is always equal to the cosine of t. That's my x position plus the sine of t as my y position. Then if I want the limit as my time is getting closer to pi over 4, I'm just going to evaluate that cosine of pi over 4. That would give me the root 2 over 2. I would do the same over here, plug that in as sine of pi over 4, also gives me root 2 over 2. All right, that would be my position at that particular time. Okay, x position, y position. All right. The continuity idea, a vector r of t, so this vector here equals f of t as your x position, g of t as your y position, is continuous at any time c if and only if the individual functions, so the x function and that y function, are continuous at that particular time as well. So when this says determine the following functions are continuous functions, what we're really just looking at is if I evaluate the x of t equation, this is really x of t right here, would there be any issues with our continuity? Hopefully we can look at that and say that the domain for t times cosine of t has no restrictions at all. So we're continuous everywhere there. This would be my y of t, my y position at any time. Similarly, there are no restrictions in our domain for this, so this should be a continuous function. So we're right now just putting a yes for this. Whereas if we go to this next one, if we look at our x position, determine if the functions are continuous functions, this x of t has a problem at the time of 0. Sine of t is fine, so the y coordinate isn't going to have any issue, but we would say no at the time of 0. All right, there's something going to be going on there if we were to try to sketch this parametrically. That would cause some sort of a discontinuity. You can do that if you'd like. Pull out your calculators. We know how to go into parametric mode. A lot of times I will have you kind of do that to see it. But since we're obviously in this situation, we're probably going to skip that. But you could pause me if you really wanted to see it and do that. All right, so we did limits. We did continuity. Next thing we did throughout the course of our year is the idea of a derivative. So we can also take the derivative of a vector. So if this vector function is given by this, all right, that is differentiable at any time if f and g have derivatives at those particular times. All right, if they do, then it's again pretty simple. The derivative of r is what this is saying. So change in my position vector over my change in time would be nothing more than the derivative of f, which is again our x position, so the derivative of the x position. And then if you look, we would just take the derivative of the g, dg, dt. And then again, this tells us that this is our x rate of change. This would tell us that this is our y rate of change. Okay. A vector function r is differentiable if it is differentiable every point in its domain. Similar stuff. It needs to be a smooth curve, continuous, and then the derivative of those both must not be a 0 or we don't have any movement at all. Okay. So first couple of these, pretty simple. I mean, doesn't really get much easier than this. If I want you to find the derivative of these vectors, you're really just doing the derivative like we normally would. And then that would be our answer. So this is my horizontal rate of change. This is my vertical rate of change, very much like the quiz we took Friday when we last saw each other. All right, that's our horizontal rate of change. That's our vertical rate of change. If I want the derivative of r here, we just get 1i plus 2x times our j. Horizontal rate of change is always 1. Our vertical rate of change is always twice x. Okay, so that first page, really, really easy. Most people don't have a real hard time with that. The back page isn't necessarily hard, but it is a little bit more involved. On the back page, you'll see it says velocity, speed, acceleration, and direction of motion. So first thing we've already kind of talked about is our velocity vector is the particle, so dr dt, so v of t is dr dt, is the particle's velocity vector, and it's tangent to the curve there. Okay, similar to what we would have talked about in the past. So it's tangent to the curve. All right, and it's just nothing more than what we just did on the previous page by taking the derivative of the x position and the y position. 2 is a big one. This we have done before, right? We talked about this a long time ago, that the absolute value of our velocity we would call our speed. All right, well, that doesn't change. All right, so you're still going to see the absolute value bars around a velocity. Back previous in the first semester, our speed was a numerical value. So we were thinking absolute values, magnitude as just that absolute value. So if our speed was a negative 10 meters per second, or velocity was a negative 10 meters per second, we would take that absolute value and we would say then that is our speed. What is now different is the idea that our velocity is no longer a numerical value. Our velocity is now a vector. Okay, just like we talked about up here. So when we do this, we still want to do the magnitude of our velocity, but since it's no longer a numerical value, if we want the magnitude of our velocity, that's what we did yesterday, if you remember. The magnitude is the length of our vector. It was the Pythagorean theorem. All right, we did that at the very end of the notes yesterday, but we're now going to be doing that with our velocity vector. So that is why, again, this was just when we did the length yesterday, it was the Pythagorean theorem, L squared equals a squared plus b squared. The length of our vector was then the square root of a squared plus b squared. But now that we're going to be doing that with our velocity vector, you're still going to be seeing the square root, but it would now be x primed of t squared plus y primed of t squared, since it's the magnitude of our velocity vector. Okay, so that one you want to kind of wrap your head around a little bit. That's harder for some people to see initially because we're used to the velocity, and this meaning absolute value is just taking that whatever negative value is and turning it into a positive. But if you really think about what absolute value means, what absolute value really means is what's the size of that number? What's the numerical value of that, regardless of if it's positive or negative? What is its magnitude? Okay, and when it's a vector, we talked yesterday, this is how you find the magnitude of a vector. Okay, we'll get into that a little bit more here. 3, if I want the acceleration, same as what it always has been. It is the second derivative of our position or the derivative of our velocity. That's what this just says here. It's a derivative of velocity, and the second derivative of position is the particle's acceleration vector. And then the last thing we want to get down of this says also for parametric equations, when asked to find the distance traveled by a particle, remember we have done distance before as well. We did it at the very end of the semester, last semester. What we would have said for our distance, we would have integrated over a certain period of time the absolute value of our velocity function. Okay, so hopefully that looks familiar. If you remember, if we didn't have these absolute value bars, we called it displacement. But when we integrated the absolute value of our velocity function, that gave us our distance. Well, this is actually the same thing. We're setting up the same thing when we are talking about vectors, when we're talking about parametric functions. Okay, but what you have to again understand is this is the magnitude of our velocity vector. So if you notice, isn't this guy here, which is the magnitude of our velocity, same as thing we talked about here, I'm still going to be setting this up, but that's what this is giving you. All right, this is the square root of dx dt squared plus dy dt squared. Okay, so we are going to integrate the absolute value, which is really our magnitude in a vector, of our velocity vector. Okay. So hopefully that makes some sense. We're really just going up here. We're integrating this over a to b. Same here. We're going to integrate this from a to b if we want the distance traveled. So this is our velocity without the integral. With the integral, it's our distance traveled. Okay. All right, let's do a few of these real quick. Number one, pretty straightforward. I give you a position vector, and then it gives you the position of a moving particle at time t. And then we want to find the velocity and acceleration vectors. So when we do this, I'm going to say r primed of t. And then we're just going to find our derivatives. This will be negative 3 sine of t. And then that's our I rate of change. And then 3 cosine of t. That's the rate of change for j. If we want the acceleration vector, we're just taking one more derivative, negative 3 cosine of t as our I position, and negative 3 sine of t as our j. That's it. If I now want the velocity at a particular time, my velocity vector at a particular time, so now I want r primed of t evaluated at pi over 4. That just means I'm going to take this guy here, and I'm going to evaluate this at pi over 4. So this is now negative 3, and then the sine of pi over 4 is root 2 over 2. It's my I position, plus, and then if I take pi over 4 and plug it in here, same thing, 3, and then root 2 over 2 as my j position. Acceleration vector is the second derivative evaluated at pi over 4. So now we're going to come up here, use this one. You're going to get some similar stuff here. Negative 3 cosine of pi over 4 is another root 2 over 2. It's my I. And then right here, plug in your pi over 4, negative 3 root 2 over 2 as our j. All right, last thing is our speed here. Again, speed, just like it was before, is we would have said absolute value of our velocity back in the day when we weren't talking parametric, when we weren't talking about vectors. We're still going to use the same exact notation, so same exact stuff, but it's just we're using different words now because we're talking about not a velocity value, but a velocity vector. So we really want the magnitude of a velocity vector. So like I talked about yesterday, mentioned it briefly here when we introduced this at the top of the paper, the magnitude of a vector is the length of that vector. So again, it's just that Pythagorean theorem, L squared equals A squared plus B squared. So this is length of a vector is always that square root of A squared plus B squared. But we're doing it with our velocity vector. So we're going to set up that square root. And what we want to be squaring, okay, we're just squaring things, is our velocity vector at that time of pi over 4. So it's this guy. All right, so that is x primed of t. All right, maybe let me write this in one time. This is our velocity vector. Okay, so let me write that in general notation, and then we'll substitute in below it. So x primed of t is what I have highlighted right there. That is at negative 3 root 2 over 2 squared. And then y primed would be, again, our velocity vectors, y rate of change, which is 3 root 2 over 2 squared. All right, so then we clean those up. So this would be what? 9 times 2 is 18 over 4. Hold on. Yeah, because if I square that, we get 9. This is a 2, so 18 over 4. This should be the same thing. 9, 3 squared is a 9. Square root that is 2, so that's 18 over 4. So what we end up getting is 36 fourths, which is a root 9. So our speed would be 3. And then no units right now, but meters per second, whatever unit of time we were dealing with. Okay, that's our speed. Okay, 2. Actually, I'm going to pause you guys a second. Okay, I'm back here. Second one starts out the same. Here is our position vector, all right, at any time. pretty straightforward. This first one, we want our velocity vector. Let's go ahead and use a velocity notation this time, even though it doesn't necessarily matter. Derivative of e to the t would again just be e to the t. That's our x position, so that's the I term. The next one, you would have had 2/9 e to the 2t times 2. Oops. So when we simplify that, that would give us 4/9 e to the 2t as our j term. So that's our horizontal rate of change, our vertical rate of change. If I wanted the acceleration vector, same process, take the derivative of each. So e to the t would just remain the same again. This would be 4/9 e to the 2t times 2, so this would give us 8/9 e to the 2t as our j. All right. And then b, finding the speed at the natural log of 3. So my speed, again, we used to say absolute value of velocity. We're going to use that same notation, but instead of now saying absolute value of velocity, it is the idea that these are finding the magnitude of our velocity vector. Okay, magnitude of a vector is the length. So we set up the whole x prime squared plus y prime squared underneath that square root. All right, we want to do this at the natural log of 3. So this is x prime, so I'm going to go ahead and do the e to the t, except our t is going to be this natural log of 3. When we go to do our y primed, here is our y prime, so that 4/9 e to the 2 ln of 3. All right. I don't remember if this works out nicely or not. I don't have the key with me. Looks promising though, so that's going to give us a 9 as we simplify that. Plus this would be 4/9. When these cancel, the 3 should get squared, so this is a 9. Oh yeah. So that's a 9 plus squared. Yeah, so 16. Square root of 25 is 5. So that is our speed. Okay. And then our distance is the integration of our speed. Okay, over whatever time period we're concerned about. So in this case, we're going to be going from 0 to 2. Again, it's our velocity vector that we want to be integrating. So we're going to do that e to the t squared. And again, here is this 4/9 e to the 2t squared. I would strongly suggest plugging these in. These get pretty ugly. You got a lot of parentheses to worry about within the calculator, ugly square roots. Just have a method to do this if you want to clean this up a little bit. First, write it as e to the 2t. If you wanted to square that guy, eliminate some parentheses. It's really up to you. I don't have my key with me. It's at school. I don't have my calculator with me to throw that in. So I'm going to leave this to you. If you're really curious, when I'm back, hopefully tomorrow, I can tell you what that is. You can excuse me. You can confirm that it's right or not. A few people want to throw it in, and compare. That's fine too. But I'm not sure what that is. All right, but that's how you set it up. All right. Next page was an old AP question, really old AP question, but I like it. It's pretty straightforward. It's simple. It kind of gets at everything that we want to get at. So during the time period from 0 to 6 seconds, particle moves along the path given by, and then they give you this, and then this, and then it asks find the position of the particle at the time of 2.5. So this is our position for x. This is our position for y. So all we really want is what is my x position at 5/2 or 2.5. So that means I really want 3 cosine of 5 pi. Then I want the same thing for my y position at 5/2. So that would be 5 sine of 5/2 pi. And then whatever that evaluates to be, those are going to be our positions. Sorry. All right. So 5 pi over 2. Yeah, test myself a little bit. Is that pi over 2? The cosine up there is 0, I think. I'm delusional right now, but yeah, I'm pretty sure 5 pi over 2, yeah, is 0. And then if we want the y coordinate at 5 halves, then this would be the y coordinate at 5 pi over 2. So that's just up here at the pi over 2. So that's going to be a 1. So then my y position is 5. Okay, you can leave it like that. If you want to write it as a point, it's at the point 0, comma 5. All right, so this is where we are at that time. Okay, letter B, you don't have an axis provided, but it wants you to sketch the graph of the path of the particle from 0 to 6. If we look at this, this is what we quizzed on already. We should recognize this as an ellipse. X is paired with the cosine, y is paired with the sine, so it should be going counterclockwise, just like the unit circle. We should be getting stretched horizontally 3, so I'm actually going to use this little graph up here. 3, negative 3. We should be getting stretched vertically to 5 and negative 5. And then again, since the x is paired with cosine, y is paired with sine, just like the unit circle, we know we're going to be going counterclockwise. So I'll just say that is the answer to letter B right there. All right, it's an ellipse that's stretched vertically. All right, C, I like to kind of look at how many times does the particle pass through the point found in part A. So we have this point here in part A is 0, 5. Typically, I would have people kind of think this one through. It's a little bit different of a question than you've been asked before, and I kind of like you to think those through a little bit. So when you see those on tests and such, you're used to kind of thinking that through. So if you wanted to kind of think that through, pause me, see if you can figure that out. But we're going around in the shape of an ellipse. This is sort of implying that we would have gone through this point 0, 5 more than once. The way the question is written, how many times does the particle pass through the point found in part A? All right, which is that 0, 5. I'm just going to jump right in. If you did want to think it through, you can pause me. But it says, how many times the particle passed through that point? So there's really a couple ways to think of this. One of the ways is to think, when did my x position have a value of 0? Or when does my y position have a value of 5? While this is sound, I would be careful of this one because there's a couple of places where your x position would be 0. Certainly here, but also down here. And these obviously are not times that we would be looking for when we're at 0, negative 5. So I'm going to not do this one, even though it's a valid thought. It would just imply a little more thinking, a little bit more processing and work. Versus this one, when my y position is 5, I'm only going to have that right here. Okay? So what I'm going to do is take this y position, so this guy here, and we're going to figure out when it equaled 5. So I'm going to take that. Now I got to remember what it was here. 5 sine of pi t. What is it? Sine of pi t. And ask it, at what time do you equal a 5? We'll divide by 5, so we're really looking for the sine of pi t to equal a 1. Understand how we would solve these trig equations here. This is really asking the sine of what angle would equal a 1. So if I wanted to know the sine of what angle has a value of 1, that is this guy up here, okay? And that is our pi over a 2. So if this little expression here, pi t equals pi over 2, that would ensure that we're at the point that we're asking about in part A. So when we look at this, the pi's would simply cancel, and we're going to be at that point at the time of 1/2. So that's the first one. However, we could continue around, and we end up at this point at 5 pi over a2. So if this little expression here is equivalent to 5 pi over 2, we are again going to end up at that point. So the pi's are going to cancel. Notice how we get a second answer of 5/2. Well, that would then imply we can just go around as many times as we want. So now the next one is going to take us to 9 pi over t. So if this little composite here, pi over t, is equal to 9 pi over 2, we're still good. So these pi's would cancel, and now I'm going to get 4.5. All right, well, if you're understanding this, wouldn't this just go on forever and ever and ever and ever? So if I did it one more time, so let's do one more, if that pi over t would equal 13 pi over 2, pi's would cancel. Now my t is 6.5. This is where we would stop. So I would not want to be boxing this and saying that this is an answer. This is the first time where we would just stop. And the reason that that is telling us to stop is because of the interval of time that you were given where this function or whatever this was moving. Whatever this particle was only moving over the interval of 0 to 6. So as soon as we get a time that is greater than 6, we know we would stop, and we would say 3 different times that that particle had gone through 0.05. Okay? All right, and then last but not least, the two things that are kind of new here from this section, find the velocity vector for the particle. So velocity vector, that's pretty simple. My velocity vector at any time t, pretty straightforward. You're just going to take the derivative. Oops, let's go on there. The derivative of this guy. You're going to take the derivative of that guy. I'm actually going to leave you that. I know you can do that. You don't need to listen to my voice tell you how to do that. You're just going to take the derivative of each of those. Although, actually, I lied. So here's something that we want to talk about. They gave you parametric equations up here. There was no mention of vectors anywhere in the setup of the problem. No mention of vectors in A, B, and C. A, B, and C were basically parametrics, things that we've already quizzed on. But then they throw out in letter D the word vector. So that's what I've kind of been talking about through these videos is vectors are parametric equations and vice versa. Just different ways of expressing motion, a horizontal motion and a vertical motion along the same time period. Okay. So when they say velocity vector, they don't necessarily use the ij notation. So you have a choice here. So let me go ahead and show this. I'm going to take the derivative of this first one. So that would be what? We would first get the 3. The derivative of cosine would be a negative sine of pi t, and then I would have to multiply by pi. So you now have two options. One of them would be to put the little I right here to indicate that this is a vector. And then let me go to the second one. So now I'm going to take the derivative of the y. And that would be 5 pi cosine of pi t. And then I could put that little j right there. All right, it's valid. It would work. What they also are okay with here, and I've seen this more and more recently, is they're going to use these little, instead of parentheses, to indicate that this is a vector. These little vector caret things here, so they're kind of parentheses, but they're little carets. So where you could write this now as negative 3 pi sine of pi t, and then you just do comma, and then 5 pi cosine of pi t. So these two things mean the exact same thing. Okay? All right, and then last but not least, write and evaluate an integral expression in terms of sine and cosine that gives the distance this particle travels. So I'm just going to create some space here so I can see this. I wrote too large anyway. All right, so letter E. The distance is the integration, in this case, from 1.25 to 1.75. The way we find distance is we integrate what we would have said before, the absolute value of the velocity. But now that is a vector, so we want the magnitude of our velocity vector. All right, you would have just found that in part D. All right, so again, it's just the derivative of these, so it's being negative 3 pi sine of pi t. squared plus, do the same thing with the y's here. That was what? 5 pi cosine of pi t. All right, let me just double check that real quick before I sign off. Yeah. Again, I don't know what that answer is. I don't have my calculator. These are not easy to plug in. You can see there's a mess here, bunch of parentheses. Easy to kind of mess up your order of operations with that square of each of those terms, with the square all being underneath that square root. So kind of ugly. I can share out those answers tomorrow, hopefully, if I am there, to make sure that you got those correct. But other than that, it's really just plugging into your calculator. So hopefully that makes some sense. I rushed a little bit here. And again, hopefully I'll see you guys tomorrow.